Bob Center of Northern Lights. He's been active in yachting for 49 years and started a member of the Explorers Club in Portland, Oregon, Sea Explorers. Owned boats for 38 years, lived aboard off and on. Received his degree in diesel and automotive technology from Oregon Technical Institute. In 1991, Bob joined Edge Diagnostic Systems in Sunnyvale, a Silicon Valley startup specializing in PC-based live electronic computer signal diagnostics for gas and diesel engines. It's quite a subject area to be a specialist in. 1998, Bob founded Marine Engineering Consulting and Training. He has trained everyone from private boat owners to the Mexican Navy in engine generation systems repair and maintenance. And he's also served as an engineer on call while taking part in Nordhaven's Atlantic Rally, crossing the Atlantic with 18 motor yachts from Fort Lauderdale to Gibraltar. Let's have a nice welcome for Bob Center of Northern Lights.
Boy, this is a tough act to follow, all these good presentations here. I'm going to try and keep this extremely simple because it's one of those things where you ask someone what time it is and they tell you how to make a watch. So I'm going to avoid that if possible. This presentation is aimed at you guys, the yacht brokers, and at things that might be helpful for you to know. I'm not going to teach you how to build a generator, but mostly the fine points, things that you might be interested in. And towards the end of the presentation, we'll hopefully have a little time for questions. And I would also ask, if you would, try and find a mic if you can to ask your questions, because my ears are basically only designed for holding up sunglasses. So they don't really have any other purpose. So with that, we'll get going. I want to talk a little bit about how generators work, what they do, and then perhaps the most important thing, designing applications. That's what's important to you and your customers. Starting at the beginning, of course, I work for a small company, little company up in Seattle. You might have heard of them. They build these generators and for about the last 50 years. And anyway, we build generators from 4.5 to 800 kilowatts. And I'm going to try and be kind of generic here. I'm not supposed to make an ad out of it, but if you have questions specific to Northern Lights brand, I might be able to help. Otherwise, I probably don't have all the answers. So starting at the front, the engine we call a prime mover. And the engine is actually what controls the frequency. Frequency isn't controlled by anything except the engine speed, and it needs to run at a constant RPM. So the engine's governor maintains that RPM as the load changes. Now, the generator in your boat, the back end that makes the electricity, we call the alternator. That alternator is actually pretty similar to the alternator that's in your automobile. And if we looked at some of the parts, we'd see that the part that makes the power in the middle, that's the output stator, is pretty much the same. And your car's alternator has an exciter, a brush exciter. We use brushless exciters in generators. And the most difficult part of this, something I usually take 2 days with mechanics in classes to explain how you put the diesel in the front and the electricity comes out the back. We're going to try and do that in half an hour here. So basically, we use a voltage regulator that sends DC power to an exciter field to make an electromagnetic field that provides electricity to the main rotor, another magnetic field. It turns around and makes AC electricity. Each alternator is wound to produce a certain voltage. So there's really not too much difference between a car alternator and the alternator end on a generator. It's basically just bigger. So inside the generator, typically hidden away in a junction box somewhere, is what we call an AVR, automatic voltage regulator, and it controls the output, the AC output of the generator. So you see that. And the AVR is used in almost all generators now. Many years ago, we had generators that didn't require automatic voltage regulators. They were self-regulating. Well, self-regulating generators were a little simpler, and that's a good thing. The only problem is you don't get something for nothing. And when you would apply a large load to a self-regulating generator, you'd get a pretty big voltage dip and a pretty good voltage spike. So in the last decade or two, as the electronics came along, we found that it was really necessary to control the voltage a lot closer so as not to blow up somebody's expensive electronics. So earlier generators didn't use AVRs, later ones do, and we have very few self-regulating models on the market anymore. One critical thing about generators is how we start and stop them automatically and how you protect yourself from an expensive failure. And to do that, you have some sort of a safety shutdown and control system. So the safety shutdowns and control systems vary quite a bit. The simplest systems, made by my friends here in Seattle, just use some relays, 3 or 4 simple relays, to control the start and stop and safety shutdowns. And other systems are considerably more in depth. Some use microprocessors to go even further and to automate more functions. So there's different ways to do it, but in the end, a generator has to protect itself from overheating, from low oil pressure, and there needs to be some way to detect a stoppage in the seawater flow that cools the wet exhaust. Now, different generator manufacturers do that different ways. Some detect seawater flow, and others actually measure the exhaust temperature at the wet elbow. That's the injection elbow, where the water cools the exhaust. In some commercial large generators that we build, class requirements ask that we install a water flow sensor to detect a stoppage in the water flow. It turns out that a lot of water flow sensors are easily tricked by air bubbles or things like that. So a water flow sensor typically is attached to some sort of an annunciator or warning rather than actually shutting down the generator, at least in the Northern Lights units. So water flow sensors sometimes require maintenance, and they should be checked periodically. Perhaps the biggest thing to talk about with generators, the most important part, concerns the loading of the generator. So we have a big problem with loading, and I can't really emphasize this enough. I can't even begin to tell you how many problems it causes. I'd say for every 1,000 phone calls or emails that we get that have any kind of a problem at all, we might get one that involves not being able to carry the load, and 999 that are directly related to not enough load. So problems related directly to low load. Underloading means less than 50% load. We have a problem that we didn't used to have, and that is that, well, actually several problems. The biggest one is that at relatively low exhaust temperatures, which are caused by low generator loads, carbon forms in the exhaust system, and it can even plug up the exhaust system. That carbon also goes to other places in the exhaust system where it's collected, particularly gas-water separators, and in the case of big yachts, sometimes that carbon is actually swept out, filtered out with the water, and it appears below the water line, and then it's pretty nasty looking, And in small quantities, it forms a sheen on the water. In large quantities, of course, it looks like a big black oily mess. So this is a big deal. Low loads are a big issue. And basically, generators are designed to carry the heavy loads. Light loads should be carried by inverters or by a smaller generator, and heavy loads are carried by a generator, okay? So the main generator is designed to be 50% loaded or more. We're doing our best to convince the boat builders to go smaller now rather than too big, because we have so many problems directly related to underloading. Part of the reason we're having these problems with underloading, just to give you a little focus on it, is that emission controls over the years got tighter and tighter and tighter, and the most difficult emission byproduct to control is oxides of nitrogen. Oxides of nitrogen can be controlled a number of ways, but the way we do it in marine engines is by controlling the beginning of injection, and basically you retard the start of fuel injection. So just about every engine manufacturer uses some version of that theory. And as you retard the beginning of injection, it causes the cylinder temperatures to be lower. Well, that's good for oxides of nitrogen, but it's terrible for light loads. So at light loads, we don't have enough cylinder temperatures to do a really good job of combustion. So it's really, really important to size the generator so that it's doing some work, at least 50% load. Now, there's plenty of big boats out there that only have one generator, and we know they're going to be too lightly loaded at some point. So, as our friends at D'Angelo pointed out, there's different technologies to take care of that. You can either filter out the carbon, or you can burn it using a heated diesel particulate filter. Those things, again, are a little added cost and a little added weight. So depending on how big the boat is, how big the generator is, it might be a really good idea, or it's possible that the boat just can't accommodate a system like that. And if it's a smaller boat that can't accommodate quite that much hardware, then it's a lot more important to really look at properly sizing the generator. So we'd really like to see the generator loaded to 50% load. I've repeated that about 10 times now. So, yes, sir.
Would you define that specifically as in regular language, 5 kW, what's 50% load?
Half load, 2.5 kW. Okay. Most people convert that. They want to know how many amps that is. Question we always get. So how do you figure out what it is? I'll give you a real simple way, keep the math simple. Let's pretend you have a 12 kilowatt generator. 12 kilowatts is 12,000 watts, okay? If you divide it by the voltage that you're taking the power out at, 120 volts, you get 100 amps. So 12 kilowatts gives you 100 amps at 120 volts. So half of that would be 50 amps. So we want to see that generator loaded to 50 amps. So that makes the math easy. Just divide the kilowatts by the volts that you're using, and then you can figure out how many amps are available. So in a case where there's no room for exhaust treatment of any kind or for filtration treatment, one option is to have an automatic load bank. There's a number of people that make automatic load banks. Happens that Northern Lights owns a company that does that called Technicold, and some others as well. And an automatic load bank can substitute a heater load, a resistance load, which is just cooled by water and then pumped overboard to keep the generator at a proper load so it never gets too lightly loaded. That way a large generator that has to run with very little load on it can still maintain a proper load. Now, generators also can be built with power takeoffs, and a power takeoff usually is used for, well, can drive anything, but typically it's going to be used to drive a hydraulic pump. So hydraulic pumps have become a big deal because we use them for driving winches, thrusters, stabilizers, even emergency come-home drives on some smaller trawlers. So we actually discovered something that we didn't expect. Most of these, I'll back up here, most of these hydraulic pumps are electrically clutched, meaning you push a button and the pump is clutched on. Well, it turns out that if the pump runs continuously, it's pretty rough on one of the bearings in the electric clutch, and it can cause premature failure of the electric clutch. So stabilization at rest systems really brought this to light. And of course, stabilization at rest has become a popular option now on boats. So in an STAR, stabilization at rest system, it's desirable to cycle that pump about once an hour, at least once an hour, to rotate the bearing and get the lubricant in the bearing so that the PTO doesn't fail early. But there's a better way to do it. And the better way to do it that's used on most bigger yachts is to drive the hydraulic pump with an electric motor. That eliminates the cost and the complexity and also the noise problems that are associated with hydraulics running all the time. So if there's a choice, the best choice is to power the stabilization at rest hydraulics electrically from the generator rather than through a power takeoff. Eliminates several wear points, it saves a lot of money, uses a little less space, and it's also a lot easier to isolate that noise. The big problem with hydraulics is that once that noise becomes structure-borne, it's almost impossible to get that noise out of the structure. It's a really, really difficult noise. So it's better if you could eliminate that at the source and use an isolated electric pump. So if you have a choice, we'd like to see electric hydraulic pumps rather than PTO-driven pumps. We're going to talk a little bit about designing applications, and of course, this is all the things that you see. And we don't expect you to be extremely technical, but there are things here that you can see and touch and feel, and you can pretty well tell whether or not it's the way it ought to be. So ABYC presented their quite a good seminar first thing this morning, and a lot of boat builders claim to follow ABYC rules. And I think to some extent, many of them try to do a good job. But if you've ever seen the ABYC book, it's pretty thick. If you actually saw a paper version, it's like the Gutenberg Bible, and it takes quite a bit of interpretation, and it's very complex. So boat builders do their best to follow ABYC rules, but for various reasons, sometimes they can't do that or they don't do that. So it's a very, very good idea to make sure that, if possible, they follow the ABYC rules because they guide our way around a lot of these problems. So we're going to talk about electrical considerations, mechanical considerations, and noise, vibration, and harshness, and then serviceability. And those are all things that go into proper generator design. Any questions before we launch into this part? Okay, we'll blast right into this. I'm going to try and keep you from running late here. Okay, from the electrical side, we're concerned about the AC outputs. And if you're involved in the planning stages of a new build, this is a terrific place for you to be able to do the customer some big favors. So generators can be designed, and most generators are designed to supply two voltages, a high and a low voltage, so typically 120 and 240. So the 120 volt current is typically used for house loads or what we call hotel loads, and those would be relatively light loads, lighting and entertainment systems and so forth, but not really heavy current draws. So 120 volt is ideal for those. The 120 volt side usually is going to be from two different coils in the generator, and those need to be balanced. So we'd like to keep the 120-volt loads relatively the same. But if possible, we'd like to put all the heavy loads on 240-volt. There's a lot of good reasons for this, but without going into really deep detail, it's just generally better for practically everything. So if possible, the heavy loads like air conditioning, hot water heating, anything that's a heavy load should go on the 240-volt side. So if you can split those up that way, split the 240-volt loads at the main panel, you wind up with a generator that's more able to carry the heavy loads, and at the same time, there's less wear on the generator. It's a balanced load system. And then lastly, consider whether or not this boat might ever be running in Europe or converted to a European spec boat, meaning a different voltage and a different frequency. So say the boat possibly is going to wind up going to Europe and staying in Europe, and it'll start out as a 60 cycle American boat and then be changed to a 50 cycle European boat. This can be a very, very expensive undertaking from a conversion point of view. In fact, sometimes it's not economically feasible. So at the design stage, when you're building the boat, they may need to go with a little heavier wiring and a few other things, but if you take it into account at the beginning, then it's a relatively easy conversion at the other end. So it needs to be taken to, in the design stage in order to make it an easy conversion. From the generator standpoint, it's easy and it's not a big deal at all. From the wiring standpoint, it's a much more different situation. So bear in mind, though, that if you do anticipate this happening, the generator's output is going to be derated. It won't produce as much power at 50 cycles as it does at 60. So your 100 kW generator at 60 cycles, when you convert it to a European application, might turn into an 80 or 85 kW generator. So if you're right on the ragged edge of having enough power with 60 cycles, you're not going to have enough at 50, because your engine will take a derate when you slow it down from 1800 RPM to 1500. So good idea to take that into account in the design phase. In terms of DC requirements, battery size and wiring runs are a big deal, and on a lot of big yachts, the batteries may be located a long ways away from the mechanical equipment. This can be a problem. It's usually not too big a problem, but again, the generator manufacturers specify how long the wire runs can be, what size the cables are supposed to be. And that's in the application guides that the manufacturers supply. Now, being undersized is a big problem because it's going to be very expensive to fix it. So if you have anything at all to say about that, it'd be good to check it beforehand. Now, multiple generators sometimes suffer some sort of difficult to diagnose issues when they aren't physically grounded on the DC side with their companion generator. And they can be extremely difficult to diagnose. So one of the ABYC rules is that multiple generators have to share a common ground, and that's a DC ground that can carry the full starter load. This is no small thing. It actually could prevent a fire. So I'm sorry, I'm not supposed to say that word. They call that a rapid oxidation event sometimes. Anyway, so it's really important if there's multiple generators that they are physically grounded together with enough adequate sized wire to carry the full starter current. Now, almost everything these days is electronic. Electronic propulsion engines, electronic generators, all the control systems that go with them. Electronic grounds, the electronics guys would tell us basically bonehead electronics. Electronics 101, we know that the grounds are supposed to be consolidated. Sometimes in the process of boat building, they sort of forget about that, and they spread the grounds all around. So especially DC grounds for any kind of electronic controls need to be consolidated someplace close to the start batteries. I mean, literally at a start battery bus. And a failure to do that can cause problems that could be extremely difficult to unravel, and the problems almost never show up early in the life of the boat. They show up after the boat gets out of warranty, or, God forbid, when you guys get the boat as a brokerage boat. So this is a big deal, and a good electronics guru is worth his weight in $1,000 bills. Ventilation, our friends at D'Angelo mentioned this, and this I can't even start to overemphasize. Most manufacturers go with 30 degrees Fahrenheit above ambient, meaning if it's 70 degrees outside, they would allow the engine room to be no more than 100 degrees inside. 130 Fahrenheit maximum is not quite a standard, but it's a common standard. There are some manufacturers that don't allow that much temperature. And it's even possible you might have to air condition an engine room in order to meet their specification. So the big problem with high temperatures in the engine room is the downstream failures. So things which are never intended to be replaced or never expected to fail begin to fail. And the four categories that we see that are dead giveaway to excessive heat in the engine room are seal failures, electronics failures, automatic voltage regulator failures, and fuel injection system leaks. And those are just a great big red flag that says, hey, look over here, it's too hot, there's a problem, figure out what the problem is. So this is no small thing, and it's an epidemic right now. We have an epidemic of boats that have, shall we say, inadequate ventilation in the engine room for various reasons. There's lots of reasons for it, and there's no two boats that are alike. It may take some professional help in the ventilation to get it right, but every dollar that you spend on ventilation, it will return $1,000 in maintenance costs. So it's very, very worthwhile to make sure that the ventilation is good. A lot of people worry, okay, they overthink ventilation. Okay, they say, okay, is the pressure too high or is it too low? You know, I don't want to have too much fan speed, not enough fan speed. We're overthinking it. It's nothing that complicated. Basically, if you can't open the engine room door, it's too negative. If you can't close it, it's too positive. That's about as complicated as it is, because really the engine can live with anything in those limits. And one way to tell if you're in a properly ventilated engine room is really easy. You go there after the boat's been running for a day or 2 days. And first of all, if you can be there for more than 10 minutes and not feel like you're going to die, that's a good indication. The second indication is if it's windy. So if you're in an engine room and it's windy, it's good, okay? That's something that just about every boat shares that has good ventilation, is that it feels windy in the engine room. Okay, one of my favorite subjects, wet exhaust systems. Okay, exhaust systems are a big deal. This is not a small thing. About 50% of the generator failures are directly attributable to seawater entering the engine through the exhaust system. That's a big number. They don't wear out, they get killed. So most of these generators have a potential very, very long service life. They should live typically through a half a dozen boat owners if they're taken care of. but 50% of them will fail due to seawater entering the generator. And that's unbelievable. That means that someone from the boat builder on down really blew it in the exhaust system design. So the easy thing to remember, and what you can see when you go in the engine room, you can just use your eyes to tell you. Water does not go uphill very well. Even if exhaust is pushing it, it doesn't go uphill very well. So it needs to drop. Wherever there's water in the exhaust system, it needs to drop steadily at a minimum. This isn't a maximum, this is a minimum, ½ inch per foot. That's 2.3 degrees, okay? It needs to drop at least ½ inch per foot steadily. It can't go back uphill. It can't have a big belly. It has to continuously drop until it either gets to the muffler or until it gets to the outlet on the side or the back of the hull. So I'd say we probably see half of the new boats built that in some way don't follow that rule. That's a simple rule. It's an ABYC rule that's been with us for more than 30 years. So a boat builder doesn't understand it, well, we're not sure why. So another thing that we frequently are asked is whether or not you can put the generator exhaust into the same exhaust as the main engine, because God forbid we have more than one exhaust hole on the side of the boat. And the answer is no, you can't. You can't share the exhaust with any two engines. Every engine has to have its own exhaust. So a few people have tried to do this, and we thank them for the business. We call that a service opportunity. So anyway, it's a bad idea to share exhaust, so please don't do that. And you can see that yourself. As a broker or a salesperson, you can just follow the exhaust and see where it goes. And if you see that it's being shared with another engine, that's a big red flag. You really don't want to deal with the unhappy customer that's going to come along with that. So the exhaust also can't be reduced in diameter after it leaves the engine. That's one of the golden rules, is that we never reduce the exhaust size after it leaves the engine. Sometimes it can be increased, but it can't be reduced. So the most important thing after that is meeting the back pressure specs. Back pressure specs, as our friends from D'Angelo pointed out, vary by manufacturer. There are some fairly standard specs, but sometimes there's exceptions to the rule. So this is another place where we want to refer back to the manufacturer, get the manufacturer's recommendation. Double clamps are always required on wet exhaust systems. That's one of the few places they actually are required. We would think ABYC would require double clamps below the waterline. Actually, the ABYC rules don't. They require double clamps on the exhaust system. Another important thing, the exhaust system needs to have a way to detect an overheat situation, because just about every boat is built with exhaust systems that have flexible components, typically fiberglass, sometimes silicon rubber, but it's the fiberglass mufflers and fiberglass tubes that we're worried about, because they don't have an unlimited ability to absorb heat. And should the seawater flow ever stop, remember the exhaust temperature is going to be somewhere between 500 and 900 degrees, okay? At a little over 400 degrees, give or take, fiberglass and epoxy resin begins to soften. So if the exhaust system suffers an overheat because it lost the seawater flow and for some reason that wasn't detected, what happens right after that is very important, because all of the clamped components are then loose, because the fiberglass actually loses strength and it sort of shrinks away from the rubber. So a hose could blow off after you had this overheating event, and the seawater pump could sink the boat. And seawater pumps move a lot of water. They move enough water that it'll typically wash accumulated junk that's in the hull areas where people have never been for years. It washes that down towards the pumps, and then the pump inlets get plugged up and they stop pumping. So it's an insidious sort of a problem. And it's very important to know that it is going to happen. So the best, easiest thing to do is to have an overheat detector on the exhaust. And there's companies that make a little kit for that you can buy for about $80 that bolt right to the exhaust system within 6 inches of where the water is injected and turn on an alarm in the pilot house area. Now, this is a simple illustration of how a wet exhaust system should be plumbed, showing a couple of things that are important to you. Again, from where the exhaust is, the water is injected into the system, it needs to drop at least a foot to the muffler. And again, a steady downslope with no rises or bellies. And then it can be lifted 48 inches maximum from the bottom of the muffler up to the high point of the exhaust, and then it should drop a minimum of another foot. Where this is tricky is if it's a side exhaust in a sailboat or in a deep draft passage-making boat where there could be extreme changes in the water line, because that could negate the amount of drop that you've got there, and then the muffler could fill full of seawater, and then, of course, that seawater could back up into the engine. The other part of the system that's really important is that if the exhaust seawater is injected within a foot of the water line here, then a siphon break is required between the raw water pump and the engine. And the siphon break prevents seawater from siphoning into the engine and into the muffler. And in some cases, it could fill up the muffler, go back into the engine, into an open exhaust valve, back out the intake, and it could flood the engine room. Needless to say, that's another service opportunity for us. So this is an important point, and it's often neglected by some boat builders or people who refit. And these are things that you can see yourself. So dry exhaust systems are a little less common in small generators, but fairly common in big generators, and we do build a lot of big generators. So dry exhaust systems, again, we can't reduce the pipe size after it leaves the engine, but something a little trickier, we can't support any weight on the turbocharger exhaust elbow. That weight has to be supported either by bracketing in the exhaust system or from overhead with a flexible connection. This is really important. It contributes a lot to noise that's noticed throughout the boat. So the exhaust system will fall apart if it's not supported that way. A vibration will definitely shake it apart. So no weight can be supported on the exhaust outlet at the turbocharger. And lagging in the insulation can't exceed 200 degrees at maximum load. 200 degrees is a pretty high temperature. It would be nice if it was less than that, but 200 degrees is the absolute maximum. And of course, it has to meet the back pressure specs. So in terms of fuel systems, we need adequately sized filters and plumbing. The Racors, again, we can't share, so primary filters can't be shared. So if you've seen a refit, for instance, make sure that in the refit, they haven't tapped into some other system's fuel filters for the generator. This is an easy enough mistake to make, but it's not allowed by any manufacturer. And then a really tricky one, especially on the bigger boats where the tanks are a little ways away from the generator. If you have to lift the fuel more than 30 inches, it's really necessary to have a supplemental pump, a supplemental fuel pump. Because 30 inches is pretty much the practical limit on lifting just with the engine's lift pump. So That's kind of an important thing, and it causes long crank times and typically will cause low generator output. The generator won't carry quite as much load, but the generator guy comes by and says, gee, I can't find anything wrong with the generator. So it's particularly in a refit, you might get into that. And then we get into NVH considerations. NVH is an acronym for noise, vibration, and harshness. And many times we find somebody wants to mount a smaller generator along with a bigger generator, but there's not too much room in the engine room, so they create some sort of a bracket or some device where they can mount one generator piggybacked on top of the other. And they'll build a frame for that. So when you have stacked sets, not only do you have to allow room for servicing the generator below it, but you have to be very, very certain that when that stacked generator was installed, that no part of it or any of the bracketing touches the aft bulkhead or the side bulkhead in the engine room, because that will create a drumhead effect, and all that noise will be carried throughout the boat, and it's almost impossible to get rid of it. So you can't have any connection to a bulkhead from that frame that carries the generator, and that's a fairly common mistake on refits. So when a generator is mounted, especially a big generator, we're talking over 50 kW generators, if it's possible, we want that generator mounted parallel with the center line of the boat, okay? The reason for that is that the generator's rotating components weigh hundreds of pounds. And if the generator is mounted athwartship, those components are going to want to move back and forth as the boat rolls, and it can take out the rear generator bearing and destroy the thrust bearings in the engine. So a better way to do it would be to mount big generators parallel with the center line. Smaller generators don't really have that problem, so don't get too worked up about it when you see small generators mounted that way. It doesn't usually cause an issue. But big generators, we really, really need those generators to be mounted parallel with the center line of the boat. Now, one thing that's very popular is compound mounts or double isolation mounts. So in a compound mount situation, the generator's mounts are supplied by the manufacturer, but then there can be a second set of mounts that the generator's base is mounted on, and that second set of mounts is critical. So you can't make any assumptions. This is someplace where really you should contact the generator manufacturer and say, hey, I'm going to run compound mounts. What mounts do I use? And it's very, very possible to double the amount of noise and vibration from the generator by not selecting the right mounts. So it's really important to get the generator manufacturer's input on those mounts. And it's not intuitive. We would think that, okay, we should have really soft mounts under the generator. Actually, the reverse is true. The soft mounts go inside the generator. The harder mounts go between the generator and the boat. But getting that right is a place where you need some help from the manufacturer, and all the manufacturers can supply you that information. Finally, the last thing is serviceability, and serviceability is a really huge indicator of maintenance costs. So we want to provide unrestricted access so the engine has, the generator has good ventilation, and the service points are easy to reach. And different generators have different service points, but typically a generator is assembled with what's called a service side, where the most commonly serviced items are. So the service side needs fairly unrestricted access. And you need to verify, and again, this depends on the manufacturer of the generator, that there is actually enough space to do routine service items, particularly heat exchangers. Heat exchangers will get the most service. And it's quite possible in some models that require 2 or 3 feet of space in front of the generator to get the heat exchanger out, that if that space weren't there, it would be necessary to remove the entire exhaust manifold and turbo and lift the whole thing over the engine in order to get the heat exchanger out. And someone's going to be very unhappy about that. So at the planning stages, this is where you deal with those problems. So make sure that there's enough serviceability space, particularly for heat exchanger service. And the starter is typically on the non-service side, so it'd be really nice if you didn't have to physically remove the generator from its mounts in order to change the starter. So it's a good idea to actually plan that much room. We had a problem with a major yacht builder that buys lots of Northern Lights generators, and they built 10 50-meter yachts with pair 99 kW generators. And all of a sudden, our auxiliary electric cooling fans and those sound enclosures started falling off. Kind of an unusual thing. So they would melt and fall off. And it turns out in checking that they'd only allowed about 1.5 inches of clearance between the backside of the generator and the bulkhead. And that happens to be where the generator's ventilation slots are. All the ventilation occurs on the backside. So you have to make sure you haven't obstructed the ventilation, even though it's nice to make room in the engine room, you still have to have ventilation. Lastly, and perhaps most important, verify in the ventilation that there's no source of water, spray, seawater anywhere near the unit. And this is particularly important in a generator that's mounted in a lazarette. So we see a lot of lazarette-mounted generators where they come to grief because they've got seawater dripping on them. So ideally, you'd mount so that it couldn't possibly get seawater on it. Thank you all for enduring this. And if you have any questions, have a good day.
We have time for a couple of questions. Anybody? Back over here.
Is it possible to sync two smaller generators together as opposed to having one larger generator?
Could you repeat that?
Do you mean electrically parallel them? Paralleling is possible. On smaller generators, though, it's not always desirable because of the cost of the equipment. So sometimes the paralleling equipment can approach the cost of the generator in small units. In larger units, we do it all the time, so it's no big deal at all. But typically, paralleling is done on 50 kW and up machines. A lot of boats now are using smaller generators as a night generator. So that small generator can then just be connected to exactly the same bus as the main generator. You just can't run them both at the same time. So yes, you can, but no, you can't.
Over here.
Pardon me. You know, with all these new electronic control panels that we've seen and electronic control panels and monitoring panels, and a lot of the generator starts are started through this electronic componentry. Are there built-in hard starts, or can we get built-in hard start that in the case that you have a failure with your control system, that you can get power to the ship in a tough situation?
I'm not sure I got all of that.
Okay. Most everything is electronic controls. You got big panels and circuits you got to go through to switch your load, to go from Gen 1 to Gen 2, etc. But if that componentry fails, I thought, and again, it's lack of knowledge, but it's isn't there what called sometimes is built in as a hard start, so that you bypass the electronic touchboard, key screens, and all that stuff, and go directly to your little lugger engine and start it up.
Okay, if I understand your question about bypassing electronic controls between the pilot house or helm station and the generator so that you can start the generator locally, yes, that's easy to do. typically just have a local panel teed in right at the generator. That's easy and inexpensive. However, electronic engines won't run in the event of the failure of the ECU, electronic control unit. So if that's what you meant, you can't do that, unfortunately.
Thank you.
Got time for one more question. Anybody? Right over here. One more, please.
Do you see LNG fuel in the future?
Didn't understand what you said.
LNG fuel in the future. Let me see.
Natural gas. Oh, natural gas?
Yes.
Boy, it's hard to say. It's not that difficult to do. To my knowledge, though, there is not a great deal of energy going into that right now. So it's been pretty well perfected on highway vehicles, but so far we don't have too much of it in generators. So I wouldn't be surprised to see changes in the future, but right now there's really not much to talk about.
Thanks, Bob. Bob Spencer, Northern Lights, thanks so much.
Thank you.